Okay, let's continue with this discussion about the mole. This is extremely important, and I'm going to show you now in a series of slides the relationship between these things so that you can see why they're so important. If the daily requirement of potassium is 4.7 grams, what is the requirement in moles? Well, the way to find that is shown right here. You start out with the mass of potassium, which is measured in grams, in this case 4.7. You divide that by the molar mass of potassium, which if you look it up on your periodic table, you'll find that that's 39.1 grams. And when you do the division, you end up with the moles of potassium atoms. And you'll notice that when you divide, the grams cancel each other out and you're left with moles. Now what you can also say, once you have the moles of potassium atoms, if you multiply that mole number by 6.02, that you have exactly that many atoms of potassium. So the molar mass, as I said, is 39.1 grams per mole. And you take that mass and divide it by the molar mass, so you take 4.7 grams divided by 39.1 grams per mole, and you end up with 0.12 moles of potassium. A liter of air has 0.00092 moles of argon. What is the mass of argon in a liter of air? So how do we do that? Well, we start out, we know that we have a certain number of moles of argon atoms. We multiply that by the molar mass, which is grams per mole, and we end up with the mass of argon atoms in grams. Again, you'll notice that the mole in this case, in the labels, cancel each other out, and you're left with the grams. So the molar mass of argon is the atomic mass expressed in grams. You look it up on the table and it's 39.95 grams per mole. So you take the moles of argon atoms times the molar mass of argon. So 0.00092 times 39.95 grams per mole, and you end up with 0.037 grams of argon in a liter of air. How many copper atoms are in 5 grams of copper? Now this requires 2 steps. You cannot take 5 grams of copper and know how many grams are in that by any single operation. The first thing you have to do is say, well, I know how many atoms are in a mole of copper, so I need to convert this to moles of copper. So here's the diagram. So on the left here, you start out by converting mass to moles. And then once you know how many moles you have, you know there are exactly 1 Avogadro's number worth of atoms in a mole. And that gives you the number of atoms. And so the calculation goes as follows. The molar mass of copper, you look up on the periodic table, and it shows you that it's 63.55 grams per mole. You multiply that mass of copper divided by the molar mass of copper, that's the first operation on the left, times Avogadro's number, and that tells you total what the number of atoms there are. So you take 5 grams divided by 63.55, that gives you the middle section, or the moles of copper atoms. Then you multiply that by the number of atoms per mole, and you end up, there are 4.74 times 10 to the 22 atoms of copper in 5 grams of copper. Now you see what you've done here. You've converted a mass, 5 grams, into the number of atoms, which you can't measure. But you can measure 5 grams of copper, and when you measure 5 grams of copper, you know you have exactly this many atoms. So this, as you'll see in the future lectures, this is extremely important because this tells you, how many atoms are available to react with other substances in a chemical equation. How many moles of glycine are in 28.35 grams of glycine? Now, obviously you can't do this unless you know the formula for glycine. And the formula for glycine is given here, C2H5O2N. You have to find the formula mass for glycine, which we just did a little bit ago on how to do that. And once you find the formula mass or molecular mass, then you divide that into the mass you have, and that tells you how many moles you have. So you take the mass of glycine in grams and divide it by the molar mass of glycine, which gives you the moles of glycine. And that's this calculation here. There's 2 carbons, so 2 times 12.01, which is 24.02. 5 hydrogens, so 5 times 1.008, or 5.040. 2 times 16 for the oxygen, and 1 times 14.007 for nitrogen. You add all that up and you get 75.07. You then take that number and divide it into the mass that you have, which was 28.35, and you find that you have 0.378 moles of glycine. Now, if you multiplied that 0.378 times 6.02 times 10 to the 23rd, it would tell you how many molecules. A daily allowance for vitamin C, given here, is 0.000142 moles. What is this in grams? Since I've given you the formula here, I'm going to let you stop the tape and do the calculation and see if you get the right answer. Remember, the first thing you have to find is the formula mass or molecular mass for vitamin C from its formula. Then you have to multiply that by the number of moles you have, and this will tell you how many grams there are in the daily allowance for vitamin C. So stop the tape and do the calculation on a piece of paper and see what you get. So the molar mass times the moles of vitamin C times the molar mass will tell you the mass of vitamin C. So 0.000142 moles times, and inside the square brackets here is the calculation of the molar mass for vitamin C. So it's 12.01, I just rounded it to 12, times 6 plus, and 1.0008 times 8, and I rounded it to just 1, and then 16 times 6. And if you do the math here, you end up with 0.025 grams of vitamin C, or 25 milligrams of vitamin C. And here's the diagram that shows how you would find that. This is a much more complicated molecule. This is saccharin, and a single packet of saccharin has 40 milligrams in it. How many molecules of saccharin is this? Saccharin, by the way, is the sweeteners. You have the pink stuff, the blue stuff, and the yellow stuff. And the pink stuff is saccharin. The blue stuff is NutraSweet, and I can't remember what the yellow stuff is. But this is an artificial sweetener, and a packet has 40 milligrams in it. So how many molecules of saccharin is this? So first of all, I have to tell you, well, you had the diagram. Here's the formula for saccharin written out. You take that mass and divide it by the molar mass for saccharin, and that gives you the moles. Once you know how many moles you have, then you multiply that by Avogadro's number, and that tells you the number of molecules that you have. So the molar mass of saccharin I've calculated here. The carbon is 12 times 7, or if you wanted to, you could put 12.01. The hydrogen is 1.008 or 1 times 5. The nitrogen is 14.007 or 14 times 1. The oxygen is 16 times 3, and then the sulfur is 32 times 1. And if you do all of that calculation, you get 183.18. So that's the molar mass or formula mass for saccharin. Then you take, now remember, it's 40 milligrams, which is 0.04 grams of saccharin, divided by the molar mass, which will give you the moles of saccharin, multiplied by Avogadro's number, tells you the number of molecules of saccharin. And it's 1.31 times 10 to the 20 molecules of saccharin. Now we'll finish up by talking about percentage composition. The percentage composition is the percentage by mass of each element in a compound. The key word here is by mass. So the calculation of percentage composition is dependent upon the mass of each element that's in a compound. So the percentage composition, you see that the percent of any particular element is the grams of that element divided by the total grams in the compound times 100. Now there are actually two ways to calculate the percentage composition. First of all, and the easiest way is actually at the bottom here. It's from the chemical formula of that substance. If you have the chemical formula, you can use the mole ratios, which I'll show you in just a minute, and calculate the percentage composition of each substance. The other way to do that is if you don't have the formula, you can take the experimental masses of each element and divide it by the total for each compound, for the compound. So I'll show you examples of both of these as we go along. So this is an example where we are doing the calculation based on experimental evidence. So analysis of a sample of a compound indicates that it has 1.04 grams of potassium, 0.7 grams of chromium, and 0.86 grams of oxygen. So what is the percentage composition? So you'll find a percentage for each of these three elements within this compound. And this is how you do it. First of all, you have to know the total for the compound, and it's 2.06. You just add up the three amounts. And then the percentage of each one is each single amount divided by the total times 100. So for potassium, it's 1.04 divided by 2.6 times 100. For chromium, it's 0.7 divided by 2.6 times 100. And then for oxygen, it's 0.68 divided by 2.6 times 100. So the percentage composition for this compound is 40% potassium, 26.9% chromium, and 33.1% oxygen. And that composition is by mass. Now, in order to use the formula, the formula mass to do this, and from the formula of the substance, first you have to have the formula. So what's the percentage composition? This is ethanol, C2H5OH. So you have 2 carbons, 6 hydrogens, and 1 oxygen. So how would you find the percentage composition of that? First of all, you would find the total, which is the molar mass, 12 times 2 plus 6 times 1 plus 16 times 1, or 46 grams per mole. Then you would do this to find the percent composition. There's 12 times 2, or 24 total grams of carbon in the 46 grams of ethanol, so 24 divided by 46 times 100, or 52%. There's 6 grams of hydrogen in the total of 46, or 6 divided by 46 times 100, or 13% hydrogen. And then lastly, there's 16 grams of oxygen, or 16 divided by 46 times 100, or 35% oxygen. So there's 52% carbon, 13% hydrogen, and 35% oxygen in ethanol.